Yeah, thank you, Anno, and thanks to the organizers and program committee for allowing me to present once again what we are doing with LLVM on the IBM C systems, or System Z, how it used to be called and how the backend is currently called, just in case you're confused. So those of you who have been to prior EuroLLVM conferences may have noticed that I have already talked twice about that topic. So 4 years ago, when we first introduced the System Z backend, and again 2 years ago when we first added support for the new vector facility in the C13 mainframe, which you see right here on this chart. In both of these talks, I talked sort of about the functional part, what we did to enable those facilities in LLVM. I didn't talk very much about performance, and this talk is now going to be about that exact topic, performance of code generated by LLVM, where we are and what we did. And as sort of, there's sort of two broad topics when you're talking about performance. First of all, is making sure that you exploit on an architecture level, like instruction set architecture, you exploit all the instructions that your target has. And on the other hand, on the microarchitecture side, to make sure that the way you lay out those instructions and use them is optimized for how they are actually implemented in any particular processor. And that's sort of, those are the two basically halves of this talk. But before going into details, sort of, first of all, why are we talking about that? And that's pretty much because of this chart. That sort of depicts performance of LLVM on Z systems or System Z. It doesn't say on the chart for various reasons, but that's just spec in 2006 benchmark numbers. And the line at the very top of that screen here, where it says 0%, this is actually our comparison baseline, which just happens to be current GCC. So GCC mainline checked out just about a week ago. That's the 0% line. And against that comparison, we did measurements on the same system. It's a current mainframe, a C13 mainframe, with all the same operating system and all the environment exactly the same, but just sort of checking out all the LLVM revisions in history that actually support System Z, starting with LLVM 3.3 when we first added that backend, and then all the way up through LLVM 4.0, which has just been released. Build the compiler, run the benchmark on the same machine, same environment, same software, everything else the same, and that's the results that we get. And of course, parts of which we knew already, some parts of that were surprising to us as well. And what I'm trying to do is now sort of, what is it that we did in order to achieve that? And if you look at that, where we started out with 20% worse than where we are today, it's quite an improvement in compiler terms, I'd say. So what is it that we did? And is there still room for further improvement? Now, if you have read sort of the abstract, when I submitted this talk, I said, now we finally matched GCC performance. If you look very closely, you see, unfortunately, we are still below the 0% line. So right now, GCC 7 is still about 1% or 1 point something percent better than LLVM. However, when I submitted the talk back in January, we actually did match GCC, but GCC has fixed the regression since, and they got another % back. So, but we'll see where we go. Just briefly, LLVM 3.3, as I said, was the initial release where we didn't focus on performance at all. So it supported only the C10 machine, which is sort of 4 machine generations back compared to the machine where we are now running on. And there was basically, we got it in just in time to make sure that it was functionally correct and everything was working fine, but there was no, has been no effort spent at all on performance. So that changed with 3.4, where we sort of, that was the first big step where we tried to make sure that most of the ISA on that old machine was actually fully exploited, and where we also started looking into exploiting more recent machines. And that continued on over 3.5, where we don't see a lot of changes anymore. In 3.6, there was actually no change at all in the backend. We still see a slight uptick. That must have been some changes in common code, and the common LLVM optimizers, I guess. With 3.7 was the big change to add the vector ISA support, which I'm not going to talk about today because I did talk about that 2 years ago. 2.8, again, only small improvements. With 3.9, we did a few improvements. Unfortunately, performance dropped. That was one of the surprises here because we hadn't noticed regressions while we were measuring each of those changes as we did them. So either we missed something or something combined in some unfortunate way, or there were some common code changes. In any case, we had a regression with 3.9, and we are currently still trying to figure out what exactly happened there and what we can do that. But with 4.0, not only did we get that back, but we got a whole lot of further improvements, and that is because this is the first LLVM release where we actually did focus on microarchitecture tuning, starting with an instruction scheduler and various other things I'll be going in during this talk. Okay, so that's where we are, and now let's get into a little bit details. And I'll try to talk about what we did based on some examples of what we needed to do on our hardware to get good performance, and what we had to do in LLVM to get that implemented, and where that was easy and where it was not so easy given sort of the overall structure of LLVM in which we have to work. So first of all, because not everybody may be familiar with the C systems architecture in the first place, this is the so-called IBM mainframe architecture, which has been going for a long time. It's probably, to my knowledge, the oldest instruction set architecture in history that is still in use. So it was introduced by IBM in the 1960s already, back then called System 360. It has been going through some iterations and renamings over the years, with the very latest iteration, which is now already 17 years old as well, called Z architecture. And the main new thing in the Z architecture was that it was now the 64-bit version of the platforms. Actually, the very first platforms had a 24-bit addressing mode, and then with the 370XA, we got the 31-bit addressing mode. So when people ask why is it 31 and not 32, it's the 1 bit that tells you it's not 24. So, and now with C architecture, of course, we have 64-bit. Within the C architecture, we are again already in the 11th edition of the architecture. So there's been 11 iterations, pretty much each of which corresponding to one new processor, or in some cases, a minor change within the processor. LLVM supports those 4 editions listed right here, which correspond to the last 4 generations of the C machine, covering about the last, I don't know, 8 years or so. So if you do have a mainframe, most likely it will be one of those. Now, how does the C architecture look like? That's another thing that I've been hearing several times. Just to clear up the confusion, this is not Power or PowerPC. It's also an IBM processor, but it's a completely separate architecture. So we have Power, that's true, but we also have the Z architecture, which is a completely separate architecture. General overview, I mean, it looks sort of pretty normal, general purpose instruction architecture. We have, as I said, it's a 64-bit architecture. We have 16 general purpose registers. We have 16 floating point registers, which have by now been subsumed into 32 vector registers, where the old floating point registers are sort of 1/2 of the floating point registers. We have something special, which is called access registers, which you pretty much don't really care about. It's sort of like segment registers on Intel, except different. And just like segment registers on Intel, pretty much aren't ever used in Linux, except for like things like a thread pointer. Just the same way access registers aren't used on Linux, except for the thread pointer. So And there's a bunch of other stuff. The one thing that's interesting is what we call the program status word, which includes things like program counter and also a thing called a condition code, which is going to become important very soon. It's by now, it's a large instruction set. So it is a direct successor of that old System 360 architecture. So all the instructions in there, at least user space instructions, are still valid. But of course, we have now gotten a whole lot more. So depending on how you count, there's about 1,000 instructions, about 2,000 if you count all the different mnemonics. It's a very CISC style instruction set. So you do have register to register and also register to memory operations. We even have memory to memory operations. We have general purpose operations, we have floating point operations in various flavors, and we now have all sorts of vector operations as well. Right, so that was sort of the general overview. And a general overview, it looks a pretty normal architecture. So if you're familiar with Intel or Power or ARM, it's sort of like those. And like each of those has its sort of specialties. So does the C architecture have its specialties. And in particular, some of those I'll be going into a bit more detail now. And that's not to say that I want to sort of focus on that the architecture is strange, because it's just not. It just has a few special things. And I'm focusing on those because the parts that are standard are very easy to implement in LLVM, right? But those parts that are a little bit different, those are the ones where it becomes interesting in how do we implement those in LLVM. And one of those that actually is a relatively recent invention that came in with the Z196, which is 2 generations past, is what we call the hybrid register operations, where we can treat our 64-bit registers as if they were 2 32-bit registers. And that is sort of started out from the fact that we already had the 64-bit operations that operate on the full word, and we also had the 32-bit operations that operate on the low word, basically as legacy from the old days when we only had a 32-bit architecture. And now what they added is sort of another set of operations that operate on the high word. And by using these operations, you can basically operate either on the low part of the register or on the high part and leave the other word unchanged, which in effect gives you basically the double register space if you only need 32-bit values. And the intent is, of course, to provide register relief, because 16 registers is sort of the space where it would be nice to have more in some cases to avoid spilling. This is, we exploit this to some extent in LLVM, but not fully, and that's one of the areas where we have been struggling with how to do that correctly in the LLVM infrastructure. So one part is relatively easy. So we have register classes, and we model these as sub-registers. That's completely straightforward and works very nicely in LLVM. So we have the GR64 class, which is the full register. We have the GR32 class, which is the low half. We have a GRH class, which is the upper half. And then we define a special class, which we call GRX, which is simply the union of the low and high classes. And this is the class that has those 32 registers. And this is the class we offer to the register allocator. So the way it works is, if, like, say, we want to do an add immediate, iCell says, oh, I have a pseudo instruction that operates on the GRX class, and that's what we take for instruction selection. And then the register allocator goes and says, okay, I choose one of the registers in this class, which could either be a low or a high register, and then we do a post-RA pseudo expansion that looks which register did we get, and then replaces the pseudo by either the one real instruction or the other real instruction, depending on whether we operate on low or high half of the register. And that works perfectly well. What doesn't work perfectly well if we have not just one register, but 2 or 3. Because we can offer that as a pseudo with 2 times GRX as input class, but the register allocator then doesn't care and can choose any combination. So not just low and low or high and high, but it can choose low and high or high and low. And we don't actually have instructions for all of these combinations, only some of them. And that's, if we offer that pseudo, some of those combinations we can't really easily then translate into real hardware. I mean, we can always do it by a long sequences of instructions, but then you get performance regressions. And even worse, if we have things like an add with 3 register operands, where you get all 8 combinations, but only 3 of them we actually have in hardware. So what would be really nice is if we had some sort of interaction between register allocation and instruction selection, where we could tell the register allocator, well, if you want to use this instruction, don't choose the 2 or 3 operands completely independently, but sort of there's only certain combinations of subregister classes that are supported by the target, and there's no facility to do that right now. So maybe at some point we can work something out and improve the handling here. For right now, there's a couple of instructions that we just don't use because of that issue. Okay, moving on to another interesting feature of the hardware, that's the conditional instructions. So I mentioned the program status word earlier, which has a condition code, which is sort of similar to the Intel flags bit, just different. It is 2 bits, but they are not used as 2 bits. They're just used as a single value. It can be 0, 1, 2, or 3. And instructions may or may not set that condition code. And the instructions that do set it, they can set it in any way they like. There's no fixed semantics to each of these 3 values. There are certain groups or sort of conventions. Like, for example, if you compare, you get CC0 if the 2 things were equal. You get CC1 if the first operand was low. You get CC2 if the first operand was high, and you never get CC3. Now, if you do a floating point compare, it's the same, except now you can get CC3, and it means the comparison was unordered. That is, one of the operands was a nan. Now, sort of, again, still similar is if you do an add, you also get the condition code set to 0 if the result of the add is 0, to 1 if it's less than 0, to 2 if it's larger than 0. Again, sort of similar to as if you had compared the result to 0, except that you get condition code 3 if you got a signed overflow, which is very nice if you want to implement like the signed overflow flag, but it's a bit awkward if you want to use that condition code to implement where somebody has written if a plus b is equal 0, because you can't really use it without changing semantics, unless you can assume that signed overflow doesn't happen, which is a whole other different story. And so on. I'm not going through all those details, just to point out that there's many instructions set this condition code in many interesting flavors, some of which compiler doesn't really have to care about, but some of which would be really useful for the compiler, like the test and the mask, where you can say, here's a bit mask, test my register against that bit mask, and tell me if all the bits I selected are 0, or if they're all 1, or if they are mixed, but the first one was a 1, or they're mixed, but the first one was a 0, right? And using this instruction, you can do a test like, if this one flag bit is set and this other flag bit is clear, in one instruction plus a conditional branch, which is pretty nice, and which we already actually do in LLVM today. Now, once you have set the condition code, you can use it in a conditional branch. And a conditional branch basically just says branch to this other address if your condition code was 0 or 1 or 2 or 3. So you have 4 bits, each bit in the mask corresponding to one of those 4 values, and you can have any of those combinations. And that way you can do like a branch if less or equal tests for, if I had a compare tests for if I had now condition code 1 or 0, right? Apart from the branches, the same thing works also for a load-on condition, which sort of is a conditional move from register to register or from memory to register or vice versa, if the condition was set. We also have conditional, well, we sort of use branches as trap instructions so that we can create conditional traps. And there's a bunch of other instructions that we now have that don't use the condition code at all. So we can, for example, do a compare and branch in one instruction. So where the instruction just has the 2 operands that it compares, and the branch target if it's equal or less than equal, and so forth. And there's a few special cases like branch and count or load and trap. Now, why I'm mentioning all these instructions, because it's not so easy to always select of all these different flavors the particular best form given the way that the LLVM instruction selection and post-instruction selection pipeline works. So if you're familiar with sort of that part of LLVM, I've put here sort of an overview of some of the more important passes, starting with instruction selection until sort of the end of the MI phase. Now you could think that all these choices of which instruction to use should all really be part of instruction selection, but that's not true because some of them depend on register choices and other things. So, and for reasons of time, I'm not go through sort of all the details here. It's just sort of, it's been a bit of a journey to discover how to combine all those various passes in LLVM and do all the right, make all the right decisions at the right places to get really good selection of the best instruction for any particular use case. And I'm not sure we actually always have the best because there's probably still some room for improvement here. But for the remainder of the time, I really want to also mention the microarchitecture optimizations. So now microarchitecture really, as opposed to the architecture, which is all publicly documented, the microarchitecture in general is not documented in detail. However, there is a public document that's sort of an overview of the important stuff that is targeted at compiler developers, which is about 60 pages, which is quite there's quite a lot of interesting information. So if you're at all interested in how the processor works internally, there's a link in the PDF, or you can Google for that title, and you'll find that document. And I'll just have two charts out of that to show here. And again, I'm not going into all the details. So this is sort of the high-level flow of how the processor works. Again, if you're familiar with how some of the other current processors like Intel or Power work, it's not all that different. It is sort of a modern out-of-order pipeline, how it works. So you have your instruction buffers from which instructions are decoded and cracked, and then they're dispatched into issue queues, and from there they're issued out of order into the various execution units that we have, which do things like load, store, fixed point, so integer operations, and the big vector and floating point unit. Now, within those execution engines, again, sort of just giving a big overview, giving a high-level overview here, they have various substages where you can see that some of the instructions take more cycles than others because they have to go to more stages, internal pipeline stages. And this is important to model in some places where you want to know latencies, like how long does it take when you start the instruction until its result becomes available. Now, traditionally, if we go back to before we had out of order, what a compiler would try to do is it would try to model the exact details of the execution phase. Like it would show, okay, if I put instructions in this particular sequence, then they run through these units in these particular stages, cycle by cycle, and would sort of try to get an exact modeling of the execution phase. Now with out-of-order engines, and the C-systems isn't different from other modern out-of-order processes here, it's really not possible to do that because you don't have enough information in a compiler to even know when instructions are going to be dispatched into the execution phase in the first place, because it depends on things like whether certain values are in your L1 cache or not, and what else is happening in the processor. But instruction scheduling is still an important thing because, for one, you want to make sure that if you go back to this phase here, that the instruction decode engine is actually operating at full speed and feeding instructions as quickly as possible into the rest of the engine. And there are certain groupings where you can decode up to 3 instructions per cycle, but if you order it the wrong way, you can decode just 1 instruction per cycle. So getting that right can significantly help with the dispatch bandwidth. You also want to, even though you can't do exact execution phase modeling, you want to do sort of a rough balancing so you don't have 1,000 vector operations and then 1,000 integer operations, because the best out-of-order engine can't sort of look that far ahead. So you want to do some sort of rough balancing that all the units, that you have sort of offer opportunities for all of the units to do something. And then there are more specific things like this FBD thing, where, for example, we have this FBD unit here, which is used for long-running instructions like a floating point divide. And there's 2 of them on the left side and on the right side of the chip. And if you have 2 divides in sequence, you want them to be dispatched on both of those sides, because if you dispatch both of them on the same side, the second divide has to wait until the first one is finished. And similarly for integer instructions, if you have dependent instructions where one uses the result of the other one, if they are on the same side, there's a bypass that gets the result faster into the instruction that needs it, but if they are on different sides, you don't. And to some extent, you can influence those sides by making sure that they are in the same or in different decode groups. And that's what you can influence by instruction sequencing. So we do have a post-array scheduler, which is pretty much what Jonas here has been working on, which is currently implemented at the very last in my pass, because we really want to nail down those decoder groups, so there should be no code-changing pass after the scheduler at all anymore. This implements the decoder group in resource balancing and FBD steering. And this did help quite a bit, but it's not completely where we want it yet, because it's only a post-array scheduler, which it has to be because it has to really know the very exact instruction sequence. But the problem is, post-array, sometimes register allocator has taken away your degrees of freedom. So you can't swap instructions just because they use the same register. But they didn't have to use the same register had the register allocator only made other decisions. But it doesn't know that it should make other decisions. And this sort of interaction between scheduling and register allocation is sort of a big topic, and it's not really solved in a really good way in any compiler I know of. But there are certainly opportunities to improve in the current LLVM setup, or maybe even improving the LLVM setup. Basically, you have these two sort of opposite goals. We want to mix up register usage so we have more freedom to choose our correct sequence post-array. But at the same time, we certainly don't want to introduce spilling where we didn't have to, because that is so expensive that will blow away all the advantages we can get from instruction scheduling. So, area of research. Just as sort of a quick remark here, instruction scheduling is one important microarchitecture optimization, but it's not the only one. There are many other things that impact performance, and some in very unpredictable ways, and which make it hard to really sort of deterministically tune the performance. But there's just 2 that we found here that are important for our processors. So loop unrolling is very important because very short loops tend to behave erratically in some ways if sort of the loop executes so fast that the branch predictor isn't fast enough to predict the backward branches all the time correctly. And then we get into hiccups. So sometimes we make code faster, and then loops get shorter, and then execution time explodes because we run into issues like that. So we spent a long time tuning that. Right now it's looking pretty good, but it took a while. Okay, still work in progress, and we are working on it. Next big topic would be cost functions to make sure that vectorizer decisions are tuned correctly. So there's still room for improvement. Let me end with just sort of, just as an aside, we also did some other stuff that wasn't related to performance, like enabling profiling directed feedback, enabling the address sanitizer, getting LLVM working on the platform, and doing things like enabling Swift and Rust on the platform as well. Going back to performance, what are we working on right now? Next generation of the processor is coming, 12th edition. GCC support has been committed on Friday already, so LLVM will be up next. And the scheduling and microarchitecture tuning will be ongoing. And to end, I'll just leave this slide here. This is sort of the one data point, the last one, that's GCC 4 compared against, GCC 7 compared against LLVM 4, just the one. And one thing to point out here is that it's all plus minus 10%, so there's no huge differences anymore. The other thing to point out is that there are both positive and negative bars here, so if you can understand what's going on there, we have the opportunity to improve performance for both compilers, I guess. So that's what we are working on now. Thank you.
Okay, thank you.
Mm-hmm.
Given that your instruction set is pretty much the exact opposite of MIPS, I wonder if you've come across similar issues.
Well, so there was the one thing that I skipped for reasons of time. This is with the offsets here. So because we incrementally got instructions added over time, they are not all completely orthogonal. So for most instructions, we now have 20-bit signed offsets, so we can address plus and positive and negative. But for the new vector instructions, we only have unsigned offsets because they didn't fit in. So what we were seeing was that the loop strength reduction would happily introduce induction variables where every instruction was a negative offset. And then it was vectorized, and we would get load address all the time, right? So that's one thing we had to fix by preferring the unsigned offsets in the strength reduction. So yes, that's sometimes interesting. Any questions?
Yeah, in the beginning you showed your graph where you showed about 8-9% improvement from 3.9 to 4.0. Is that all that you're working in the code generator, or is it also work on more general parts of LLVM?
That's a good question, and I don't know the answer to that. So this is sort of just black box. We measured it, and that's what came out. We do know, as I said, we do know that we added the scheduler. We do know that we added the loop tuning with the strength reduction. We added some new ISA exploitation for better exploiting loading condition. So we know that in 4.0 we did a lot of stuff where for each of those changes separately, we measured that it gave 1, 2, whatever % improvement. So we know we put a lot of stuff in that added performance. Does it explain all of that? I don't know. Maybe there's some common core change. Would be nice. But I don't know the specific answer to that.
Here is some nice data about runtime performance. Do you also collect the compiler performance for these things?
So we haven't focused on that right now, so I don't have numbers. But we are not doing anything special that would, let's put it that way, compiling for our target should be in the same ballpark as compiling for other targets. We are not doing anything in the backend that should take much longer than anybody else. So, but I agree, it's an important consideration as well. It's just not one that we are focused on here. Yes. Yes, well, pretty much the whole thing from sort of starting out with just measuring wall clock time, to the performance counters that are provided by Linux, like just doing perf, to counters that the hardware has. And then, of course, I mean, since we work for the company that manufactures the processor, we actually have some very special tools. So the most specific thing is we could run, if you're looking at, if you have identified a small code sequence where we see differences, we can actually run it through a simulator that basically is the VHDL of the chip. And sometimes that surprises the hardware people, what we find then there. But yeah, so the whole spectrum.